Welcome again to Let's Talk Advanced Chemistry, Chemistry 2 with Pastor Dan. We're going to look at emissions, what we discussed before, the beginning part of this section, but we're going to take it deeper and do a little bit more thorough explanation of what the process is. Emissions are defined as the process of determining placement of electrons in an atom based on the light emitted or absorbed. Now, what we're talking about is two types of emissions. These are what we refer to as bright line emission spectrums. This is where the energy comes up, and as the energy is hit, it jumps up, and so it produces those spikes, those lines where the electrons are placed, and as they produce the energy, so those produce bright line spectrums. If they come back down, they produce a similar process, and we get what are called dark line spectrums, absorption spectrums. All right, now the equation we're going to look at here is expressed as follows: pi is equal to c over nu. We talked this before. E equals h for that little funny hat on it.
That's nu, not pi, I'm sorry.
Times nu. That nu is frequency, refers to in hertz. Hertz, mathematically work with it in per second. C is the speed of light, which is 3 times 10 to the 8th meters per second. Or if you want to make it simpler, just multiply by 1 times 10 to the 9th nanometers per meter. Gets rid of meters, put it in nanometers. 3 times 10 to the 17th nanometers per second. Lambda's wavelength, usually expressed in nanometers. A meter is 1 times 10 to the 9th nanometers, I said before. Energy is expressed in joule, and H is Planck's constant, 6.63 times 10 to the minus 34th joule times seconds. All right, so let's do a problem here. Calculate the energy of an electron if it absorbs a light emission of 425.7 nanometers. So we're going to take our first equation, nu is equal to c over lambda, where nu is unknown, c is 3 times 10 to the 8th meters per second, and lambda is 425.7 nanometers. We don't have to rewrite the equation, so just plug them in there. We want to get rid of meters, but they don't cross out. So to use the equation, 1 meter is 1 times 10 to the 9th. See, 8 times 9, that's how we get 17 if you want to do that. Meters cross out. When nanometers cross out, it's going to be 7.047 times 10 to the 14th per second. Now, if I was asking for frequency, I would change it to hertz here, but I'm not. I'm asking for energy. We'll plug it right in. E equals h times nu. E is unknown here. Planck's constant, 6.63 times 10 minus 34 joule seconds. Nu we just found, 7.047 times 10 to the 14th per second. We plug that in to the equation. Our seconds cross out. We're left in joules. Get an answer, 4.672 times 10 to the minus 10th joules. 6.63 is a constant, so it's insignificant.
That was 19th, not 10th.
So we'll go for the 4 sig figs of 4.047 to get 4.672 times 10 to the 19th joules. And that's our answer. All right. This time I want you to pause the video. Try this one on your own. You're going to work it backwards. You're going to go from joules to frequency and frequency to wavelength. All right, so give it a shot. Okay, here we go. That's our answer. The answer is 619.37 nanometers. Okay, now we can go a little bit farther now. We start with a scientist, a well-known mathematician actually, named Balmer. Now, Balmer created something called the Balmer series. He was a mathematician. He looked at atom interactions. And the main reason why I include him, besides the fact that he helped bridge the gap here to Rydberg, is he was a high school teacher at a girls' school, mathematician. So I gotta give props to my paisano, my goombas, my peeps, the high school teachers. So his original series said that the frequency is equal to a value c times one half squared minus where the electron is originally. Now, Rydberg took that further and generated what's called the Rydberg Equation, where the frequency is equal to the change in energy over Planck's constant, where we have Rydberg's constant over h times 1 where the electron is initially squared minus where the electron is finally squared. The Rydberg constant is 2.18 times 10 to the 18th joules, and N is the energy level. So N sub I is where the electron is initially, what energy level it is initially, and N sub S is where the energy electron finishes out when it either absorbs or releases energy in that way. All right. So let's do a problem. Calculate the wavelength of light needed to cause an electron to jump from the first to the third energy level. Okay, so we have Rydberg's constant over h times 1 over ni squared minus 1 over n sub f squared, where RH is 2.18 times 10 to the 18th joules. Planck's constant, 6.63 times 10 to the minus 34th. We started the first energy level, and we're going to the third energy level. So we plug that in, we get 2.18 times 10 to the 18th joules, divided by 6.63 times 10 to the minus 34th joule seconds. And we multiply that by 1 over 1 squared minus 1 over 3 squared, or 1 over 1, or 1 minus 1/9. We multiply through, we get 2.2923 times 10 to the 15th per second. Now, we didn't ask for the frequency, we asked for the wavelength. So we use nu is equal to C over lambda. We're going to solve for lambda, swap partners. Lambda is equal to C over nu. Plug our values in. And when we do 4 sig figs, and we're going to convert that to nanometers, 4 sig figs, always I specify, because there's no sig figs in here. These are all infinitely significant. So for me, just to make sure we get something consistent, always do 4 sig figs here. Convert it to nanometers. We get 102.6 nanometers, and that's our answer. And that would basically be ultraviolet. It could be microwave, but it's I don't know, cosmic wave. In that way, gamma energy, upper end of the visible spectrum. All right, this time I want you to do this on your own, like we did before. We're going to have an electron drop, so it's going to be releasing energy. What is the wavelength as it releases from the third to the second energy level? Also determine the amount of energy that is. So we're going to find E here. So we're going to find the new value, the frequency, and then solve for E. So pause the video, give it a shot. Remember, LTSWPD, if you have any questions, like, share, subscribe, comment. Any questions, let me know. All right, here's our answers. There you go, 206.7 nanometers, and that again is also UV. Let's call it UV because it's below the violet there. All right, that's it. Hopefully not too bad. Take care. God bless. Bye.